Okay, so finally in this chapter, we're going to talk about why the sky is blue. You know, the fact that we look up and we see a blue sky is perhaps one of the most elemental observations in the entire course of human history, and yet we only really understood why the sky is blue for about the last 100 years. Okay, so to help understand why the sky is in fact blue, we need to understand what happens when a photon, when a piece of electromagnetic radiation interacts with something small. Right, in the section on mirrors, and even when we were talking about refraction and sunlight hitting raindrops, we were thinking about a photon hitting a large object, right? When something where the wavelength of light was really small compared to the thing it was bouncing off of, we kind of had this geometric optics perspective of how light behaved. Some of that light got reflected, some of it got absorbed, some of it maybe went through the material, if that material was transparent, and in the process it bent, if the indices of refraction were different in the two materials. But what happens when a little packet of electromagnetic radiation hits a small particle? And what do I mean by small? Let's define a dimensionless parameter. A dimensionless parameter that characterizes the wavelength of light relative to an object. Light relative to an object that it's hitting. To an object it hits. So what do I mean by dimensionless parameter? I mean a combination of physical quantities that has no dimensions. So it's just a number. And the particular number that I'm going to define, say, is, let's choose the letter x. It doesn't matter what this letter is, to be something like maybe the circumference of an object, maybe like the circumference of a spherical object, so 2 pi times r, imagining that light is going to hit a sphere of radius r, divided by the wavelength of light that's hitting it. Right? We're not going to give this dimensionless parameter a name, right? When we were thinking about fluid flows, we had the Reynolds number. This dimensionless parameter doesn't get a name, it just helps us think about things. Okay, so when x is very big, like much, much bigger than the number 1, that's when an object is very large compared to the wavelength of light that's hitting it, right? So if r is huge compared to the wavelength, x will be a very big number, and that's the regime of our everyday experience, right? That's when this kind of geometrical optics perspective can be really quite useful. When x is some number that's close to 1, you know, maybe it's 10, maybe it's 0.1, you know, within an order of magnitude of 1, let's say. So first, let me finish writing. When x is big, this is like geometric optics. Geometric optics. When x is close to 1, what happens is that light will come in, it'll kind of interact with that object in some complicated way, and then it will get sent back out, scattering off the object in some, you know, particular set of directions. And when x is close to 1, it's a complicated process, and it's known as me-scattering. We're not going to talk about this regime very much, but it is important to a lot of the things that we observe, especially a lot of atmospheric phenomena. So tiny like specks of dust, tiny droplets of water, and like some aerosols floating in the atmosphere have the right size. They're kind of spherical particles that are like about the same wavelength as visible light for this to be important. It's kind of mathematically pretty complicated, and we're not gonna worry about it too much. But when x is very small, so when the size of the object is small compared to the wavelength of light itself, you get what's known as Rayleigh scattering. And Rayleigh scattering is ultimately what we'll need to understand why the sky is blue. Okay, so we start our story kind of in the 1860s. This is section 4.1, Tyndall and Rayleigh. So John Tyndall was an experimentalist who conducted some really kind of clever experiments where what he would do was he would suspend tiny particles in a fluid, so in like a see-through liquid like water, right? And what he found experimentally, and this was in I think 1859, found that when he shined light through a liquid at a suspension of like tiny dust particles, say, floating in these fluids, found that blue light scattered more than red light. And what do I mean by that? Like, imagine I have like a bunch of material. I'm just going to say this is filled with water, and then there's maybe some like little tiny particles floating in the water. Doesn't really matter. So what he found was that, if you take some light and shine it through, some amount of that light will just pass right through this transparent fluid, but some other amount of it will kind of scatter off in different directions. So if you have like detectors sitting around this fluid, most of the light will make it through, but you'll see some of the light kind of hit the walls over here. Okay, and what Tyndall found was that if you took red light and sent it through, really most of that red light made it all the way through, maybe just a tiny amount of it scattered off. And he found that if instead you took blue light and sent it through, well, still most of the light made it through, but just like a little bit more blue light scattered off. Okay, so the difference wasn't very large, but it was noticeable. Noticeable even by the standards of like experimental apparatus that were accessible in the 19th century. Okay. Lord Rayleigh, who's a very prominent scientist of the mid to late 1800s, studied this phenomena in a huge amount of detail. He really looked through all of the experimental data that Tyndall and others were collecting, and together with thinking about the idea that light might be an electromagnetic wave, and the theory of electromagnetism was only just being developed around these times, Rayleigh realized that he could understand Tyndall's data. Okay. And I don't want to talk too much about the details, but I just want to give you a feel for scattering of light. Okay. So when you're shining light through a substance, and you see that, most of it goes through, but some fraction of it gets scattered off, we can kind of write that as an equation. We can say that the fraction of light scattered is equal to the distance that light travels through a substance. So for instance, if we want to talk about what fraction of light is scattered by this blob of liquid with dust floating in it, well, the light has to travel through a certain distance of the fluid. So the fraction of light scattered is like the distance multiplied by the number density of scatterers. So this might be like the number of scatterers divided by the volume. So if you have dust floating in water, you've got a certain number of flecks of dust in a certain volume of space. And dividing those two things would give you this number density of scatterers. And then finally multiplied by this thing. This is the Greek letter sigma sub s. And sigma sub s is what's known as the scattering cross-section. Scattering cross-section. Okay, so this scattering cross-section is something that you can measure, right? Like if you have this Tyndall-like experimental setup, you can say, okay, light is going through this much water. There's a certain number density of scatterers, and I only observe that 99% of the light makes it through going in a straight line. 1% of the light is scattered. So 1 over 100 is the fraction of light scattered. And for instance, by making that measurement of fraction of light scattered, knowing the distance it's traveling, and knowing the number density of scatterers, you've measured this thing called the scattering cross-section. It's something that tells you, turned around, how much light will get scattered as it's moving through some substance. Okay. So what Rayleigh found, or showed, that if you have a material made of spheres of radius r, so maybe you have like little spherical bits of dust or something like that, he found that the scattering cross-section is proportional. So this thing is proportional to 6 powers of the size of the thing scattering the light. And again, this is only in the regime where the size of the object is still small compared to the wavelength of light itself. he found that it was proportional to 6 powers of the radius divided by 4 powers of the wavelength of light. Okay. So what this says is that if you send in a bunch of light, remember, say the wavelength of blue-violet light might be about 400 nanometers, and the wavelength of very red light might be something like 700 nanometers. It tells you that, since the wavelength of blue light is smaller than the wavelength of red light, the scattering cross-section, you're dividing by a smaller number, so the scattering cross-section for blue light is bigger, so it scatters more light. Okay. And if you want a precise number, we need to decide what objects we're scattering off of, and we need to do a lot of work to compute all of the kind of numerical factors that I haven't written here. And here I've just written this as a proportionality. Okay, but for instance, since the scattering cross-section scales or is proportional to 1 over 4 powers of the wavelength, so it says, suppose you have the same stuff scattering light, but you're sending in red light versus blue light. Well, using these numbers, blue light will have a scattering cross-section that is, and then this ratio, 700 over 400 times bigger, to the power 4, times bigger than the scattering cross-section of red light. Right. So if I look at this formula, I compute the scattering cross-section where lambda is 400 nanometers, and then I compute it where it's 700 nanometers, I'll find that blue light has a cross-section which is 700 over 400 to the power of 4 times bigger, and that's a little bit more than 9.3 or something like that. Okay. It's really not very much. It's really not very much. Now, Rayleigh and Tyndall's data basically showed this result, that if you have things that can scatter light, then in this regime where those things are kind of small relative to the size of the wavelength of light, then the scattering of blue light will be more than the scattering of red light. And that was kind of the status as of the late 1800s. In 1910, Einstein, of relativity fame, and another scientist named Ludwig Hopf, in about 1910, did a precise calculation, right? So they made use of what was known about quantum mechanics and special relativity, which we haven't really gotten into in this class, to not just figure out that the scattering cross-section was proportional to this wavelength to the power of -4 and the size of the scatterers to the power of 6, but they actually calculated, well, if light was being scattered off of different atoms and molecules, what numbers would you get? And how would that compare to what you would get if light was being scattered off of specks of dust or drops of water or things like this? And they showed by a true calculation that the experimental data that we could see in terms of what color does the sky look like it is, for instance, they showed by a true calculation that the experimental data for, let's just say, for the sky corresponded to scattering by not specks of dust, scattering by atoms and molecules. Right. So the thing that's scattering light in the sky is light hitting a nitrogen atom, or light hitting O2 molecules, or things like this. Okay. And I want to give you a sense of just how relatively small this scattering is. So most of the air, 80% of air is nitrogen, I think. Something like that anyway. Most of the air is nitrogen. So let's think about scattering of green light, just to pick something where I've worked out the numbers. Green light has a wavelength of 532 nanometers, so 532 times 10 to the -9 meters. And if you calculate it, the scattering cross-section of nitrogen when it's being hit by green light is, if I've done my math right, something like 5.1 times 10 to the -31. And then the units of this are meters squared. You can kind of see you might have anticipated that because wavelength has units, say, of meters, and radius has units of meters. So there's 2 powers of meters left over as the units of this scattering cross-section. Okay, so this is a tiny number. What's the number density of like nitrogen molecules in like air in the atmosphere? Well, I had to look this up. There are about, what did I write? 2 times 10 to the 25 nitrogen molecules in a cubic meter of, air at atmospheric pressure, at normal temperatures, at sea level, this kind of thing. Okay, so if we plug these numbers in to this formula that we have here, right? So we have a number density, 2 times 10 to the 25th nitrogen molecules per cubic meter. We have a scattering cross-section, and so we can figure out what fraction of light gets scattered rather than going straight through for every unit distance that that green light travels. Okay? And so plugging in all of those answers, the fraction of green light scattered per meter, so I'm going to divide through by 1 meter in this formula for the distance, scattered per meter, is about 1 part in 100,000. Okay? A tiny amount, actually, right? Like just a small, almost insignificant fraction of green light gets scattered every meter that light travels through the air, right? And green light is kind of being scattered in some intermediate amount in between red and blue. So blue light probably gets scattered about 3 times as much as green light, and red light gets scattered about 3 times less than this green light, right? But it's still like parts per 100,000 per meter, right? It's a tiny amount, but actually it's enough to make all the difference, right? Enough to make all the difference. The sky is blue. Okay, so when we look up at the sky on a bright sunny day, we see like a yellow sun and we see like a blue sky around it. What are we looking at? When we look up at a patch of sky where the sun isn't, then in fact we're seeing packets of light. We're seeing photons that could not have come in a straight line from the sun, right? All of the photons coming in a straight line from the sun so far away are going like this. So if we look at a patch of the sky where the sun isn't, we must be looking at an electromagnetic wave. We must be looking at a photon that bounced off of something, that scattered off of something on its way to us, right? And since shorter wavelength light is more likely to be scattered off of these molecules of air, what we see is a beautiful blue sky. If we look up at the sun itself, what we tend to see are wavelengths of light that didn't scatter away on the journey from the sun to our eye. So first, don't look straight at the sun, but if you did, some of the blue light that is composing the kind of overall white light that the sun is sending from itself to us, some of that blue light gets scattered away, and so what we see is an object that has kind of a yellowish tinge, because we see a little bit more of the red, yellow, orange part of its spectrum than the blue light, because some of those bits of blue light on the way to us got scattered off and went in, different directions. Whereas when we look off at some other parts of the sun, we're more likely to see these things that bounced somewhere else and got to us. Some amount of red also scatters, but about 10 times as much blue scatters, and so we see it as blue. Okay. You might wonder, actually, why do we see blue instead of purple, since purple scatters even more strongly than blue light? It kind of has to do with the fact that, first, the sun doesn't produce a uniform spectrum, so it's not sending exactly as much blue light, as green light, as red light, as purple light. Actually, it's sending mostly bluish-green light, somewhere in between green and blue. So you combine the fact that the sun's spectrum, overall, because of what temperature it's sitting at, actually, produces less violet light than blue light. And then you combine that with the particular ways that the 3 color receptors, the 3 types of cones in our eyes, actually perceive light. And the net effect is that humans perceive the color of the sky as kind of a pale, total blue shade. And in the lecture notes, I have some links to more information actually about these specialized receptor cells and how they do better and worse jobs of detecting light at different actual wavelengths. Okay. But so, we look up in the sky. If we look at the sun, we mostly see light that didn't scatter, and if we look at where the sun isn't, we mostly see light that did scatter, right? If you look up at a fluffy cloud, you're seeing a brilliant white color because those droplets of water inside the cloud do an excellent job of scattering light of all different colors around. It's not in this Rayleigh scattering regime, and instead it's just bouncing off all kinds of different colors of light. And so we see all of those colors head towards us. We see a white color, right? In addition, let me draw a sun and draw a big Earth. Draw an Earth with like an atmosphere. And I guess this is like the nighttime side of the Earth since it's away from the sun. As nighttime approaches and we're standing, hopefully not to scale, over here, what's happening is that rays from the sun have to travel through more and more atmosphere to get to us, right? During high noon, for instance, when we'd be standing over here, the sun's rays only have to go through a relatively shorter amount of atmosphere of air to get to us. But at sunset, or during sunrise, for that matter, over here, I guess, probably that's how you're standing, the light has to travel through a greater distance. And because of that, even more of the blues and violets and green light gets scattered away. Right? So even more of like the blue light that might have been headed towards us gets scattered away and bounced off. Same thing for like purple light, even more so. And so the only things that actually, not the only things, but the predominant color of light that actually makes its way all the way to us are colors in the yellows and orange and red spectrum. And that's why we see like these beautiful yellow, orange, red sunsets. Unfortunately, it's not only air molecules that can scatter light, but if you have bits of dust or pollution or things like that, that can also really effectively scatter sunlight. And so, very sadly, polluted air tends to make for even more beautiful sunsets because those small kind of particles of floating pollution can make the sky an even more vibrant shade of red. But there you have it. That is fundamentally why the sky is blue, something that we've really only deeply understood as a species for 110 years, which I think is just remarkable.